Want to easily grasp the semiconductor market trends and iSTART's product deployment? iSTART class will take you to explore the iSTART world.
In edge AI or low-power AI chips, LPUs, language processing units, almost always rely heavily on SRAM as their primary on-chip memory. This is not simply because SRAM is faster than DRAM, but because LPU inference behavior places very specific and stringent requirements on memory characteristics. The application scenarios targeted by LPUs are mostly real-time, low-latency, event-driven inference, such as image recognition, voice activation, and sensor data analysis. A common feature of these applications is that the data volume per inference is relatively small, but memory accesses must be frequent, fast, and predictable. If latency becomes unstable, even good average performance may still result in incorrect or delayed system responses. In such cases, memory access latency and stability are often more critical than the peak performance of the compute units themselves. The table illustrates the fundamental differences between SRAM and DRAM. SRAM offers low access latency, does not require refresh operations, and exhibits relatively stable power behavior. DRAM, on the other hand, is better suited for large capacity, sequential data access, but requires periodic refresh, and its latency and power consumption can fluctuate depending on usage conditions. For LPUs, these DRAM characteristics can become a source of system uncertainty. From the inference workflow perspective, when an LPU executes a model, the actual computation time usually accounts for only a small portion of the total execution time. A larger portion is spent repeatedly reading weights, feature maps, and intermediate results between different layers. If each access requires crossing chip boundaries or waiting for long memory response times, overall latency is significantly amplified. This figure shows the proportion of computation time versus memory access time during inference. It clearly indicates that, in edge inference scenarios, memory behavior is often the primary performance bottleneck. As a result, LPUs tend to integrate large amounts of SRAM on chip, allowing data to be accessed with minimal latency and at high frequency, while avoiding the unpredictability introduced by refresh operations. Even though SRAM is less favorable in terms of area and cost, it remains the most practical choice for LPU architectures. However, extensive use of SRAM also significantly increases testing complexity. In modern LPU SoCs, SRAM is no longer a single module, but is composed of many memory banks of different sizes and purposes. Some store weights, some hold intermediate data, and others are tightly coupled with specific compute units. Their access patterns, activation timing, and operating voltages can all differ. More importantly, LPUs often operate at very low voltages to achieve power efficiency. Under such conditions, SRAM marginal behavior becomes highly sensitive. Certain bits or banks may only exhibit failures under specific access patterns or particular inference workloads. If testing relies solely on traditional memory test methods that verify basic read and write functionality, it may fail to reflect the risks that occur during real inference operation. By comparing traditional SRAM test scenarios with actual LPU inference access scenarios, the differences in access frequency, access order, and voltage conditions become evident. With SRAM being widely used in LPU architectures, testing is no longer focused solely on whether memory can read and write correctly, but on selecting MBIS strategies that are appropriate for the application context. Based on the START v5 platform, iSTART-TEK enables users, through the graphical and modular design of UDA, user-defined algorithm, to quickly assemble and adjust SRAM test algorithms according to LPU product characteristics, without the need to write complex code. Building on this foundation, the MBIST Algorithm Recommendation Tool, MART, systematizes existing SRAM test experience and knowledge bases. Through interactive condition settings and AI-based weighted analysis, MART assists users in selecting more suitable MBIST algorithm combinations under multiple constraints. This approach is particularly helpful when dealing with the diverse SRAM structures and application scenarios found in LPUs, as it reduces the decision cost of algorithm selection and helps avoid potential risks caused by inappropriate test strategies. By combining UDA and MART, SRAM testing can better align with real application requirements and more effectively support LPU reliability and mass production efficiency. That concludes this episode of iSTART-TEK Elementary Classroom. Please stay tuned for more technical insights. See you next time.